You can see my screen, right? You can see my screen, right? Okay, fine. So, welcome to this class. I think in the last class we are discussing about the irreversible reactions in series. Here, one important thing is we need to find out. So here, generally, we if there is a series reactions like this is the desired product actually. So we need to find out how much is dr max by dt. Yeah, some of you, okay. So because we want the concentration of R to be maximum, you don't want the formation of S because this is undesired. So that is the derivation which we need to do. But to do this, first we need to find out what is CR max. That is the concentration of R max. If you see the graph, this is the thing. It will be if you draw a graph between the concentrations versus the time. Now you see the Ca concentration will go down because this is the raw material. Raw material initially the concentration will be high. With the time, as the reaction proceeds, the concentration of A will be decreased. R and S are the products. So the concentration of S will go on increasing. What about the concentration of R? As A is reacting, R will be formed. So the concentration, it will be increased with the time. There will be reaching a maximum concentration. Afterwards, what will happen is, since S is also formed, S is going on increasing. S is going on increasing means R should go down because for R, for S, R is the raw material. So as it forms, the concentration will go to a maximum. Then what will happen? The formation of S also will take into picture. Therefore, the concentration of R will go down. So if you see this, A concentration is going down, S concentration will go up, but R concentration reaches a maximum and then falls. So we need to find out what will be this maximum concentration. Generally, S concentration should be minimized, right? So you want your CR to be at its maximum. So you have to make sure this reaction is having a CR maximum so that you get the product, more product than the byproduct. So how to calculate this maximum? Once you find out what is CR, that is the concentration of R with respect to time, then if you differentiate that, because this is having a maximum. So if you want to find a maximum, either minimum or a maximum, what is that is? You get a differential equation, you differentiate that. A equation, if you differentiate and equate to 0, you get one maximum or a minimum. So how to find out whether it is a maximum or a minimum? Again, find out the second derivative. If your derivative value is negative, that means that you are at its maximum. If the derivative value is second derivative is positive, if the second derivative is positive, then it will be at its minimum, right? This is school chemistry, school mathematics, which you know. So we need to find out what is this particular concentration or what time. So we need to differentiate this CR, right? So that is what we do now. I'll just show you. In the previous, just I will give a recap again. We are writing for the product that is R, that is the rate of disappearance of R, rate of disappearance of A, and rate of appearance of S. So you are getting three equations. So from these three equations, we need to find out the concentration of A, R, and S. So how to do? This is a differential equation. So you have to do by integral method of analysis. then you get an expression. So first equation, if you integrate by taking all the CA terms to one side, DT terms to another side, then this is what you are taking it. Let CA not be the initial concentration of A. So when there is a CA not initial concentration, you are assuming practically there is no R and S is formed, because the entire thing is only A which is being present. So if you do that integration, then you are left with, you are coming as CA is CA naught into e power minus minus K1T. This is a very important expression from the first. So like that you get R also. R, if you do, this is the expression which you are getting, because K1CA minus K2CR, that minus K2CR you are taking this side, and you are writing K1CA, KCA, CA as this particular thing. So you are getting this expression, very important expression. So the solution for this differential equation is, if the equation is like this, the differential, the solution will be like this. If the differential equation is like this, the solution will be like this, and you need to find out what is this integration constant. So this, I think in second semester you might have studied what is this, how to do that. So if you do that and do some manipulations, that is all the like terms to one side and all the other terms to another side, then you will get this particular expression. CR is this much. CR is, I'm not going through again this, because already in the last class we derived it. So you take CA naught common outside and then write it. So this will be your final expression. CR is this huge one you get. So CA we wrote, CR also we got. Like that, CS also we need to get. To get CS, we know that initially concentration is nothing but CA plus CR plus CS. Anyhow, CR and CS, this is the final concentration, initial concentration should be equal to this. Then from this CS you can write here. So you know CA naught. CA you can write in terms of CA naught. CR also you are writing in terms of CA naught. All the terms whatever we got, CA and CD, you substitute here, then take CA naught common, and then do this what do you call LCM. And if you see this LCM, then you are left with this big equation. This is the CS equation. So now we got all the three concentrations. So CR we got, sorry, CA we got, CR we got, and CS we got. All the three concentrations with respect to the time. T is the time we got. Then if you draw the graph with all this, that graph will result, right? This graph will result. So if you look at this graph, we are having CR, it is going to a maximum and then decreasing. So we need to find out what is this CR maximum. So for that, you have to differentiate CR and then equate to 0. That is what we are doing here. Maximum concentration of R, this is the R value. This is the R. If you again take the LCM K2 minus K1, then you can put this. So you need to differentiate this with respect to the time. So to differentiate this with respect to the time and equate to 0. At maximum R formation, the condition is derivative at that particular time should be 0. Right? So if you differentiate this and equate to 0, so I am differentiating this equation. This is a constant. I have to differentiate this. So K1 CA naught by say K2 minus K1. So differential for this is minus K1 e power minus K1 T, because e power T is e power T. So minus K you are getting here. So again differential to this is minus of minus is positive, K2 e power minus K2T. Now you have to equate to 0, because at a maximum, so differential should be 0. So if you equate this 0, either this term should be 0 or this term should be 0. This term should be 0 or this term should be 0. You know that this term cannot be 0 because CA naught cannot be 0. So this term should be 0. If you equate this term, so you get k1 e power minus k1t is k2 e power minus k2t, right? So that's what we will do. So this cannot be 0 because Ca naught cannot be 0. That is the initial concentration. So if you put the other one, this is going to be 0. That is what I'm showing here. So if you take the log to this equation, log of A into B is log A plus log B. Here also log A plus log B. So if you take the differential logarithm, then what will happen? Log K2 minus K2 ET, because e power this log is only you get this upper part. So you do that. Then this is ln K2 minus ln K1. So minus is ln A minus B is ln A by B. So K2T, K1T. So if you do that, you are getting T is ln K2 by K1 divided by K2 minus K1. What is this? This is nothing but a log mean. It's not a arithmetic mean. There are different means which you get in especially chemical engineering. There can be a log, there can be a arithmetic mean. Arithmetic mean is nothing but some, if there are some A and B is the some two values, A plus B by 2 will give you arithmetic mean. There is logarithmic mean. Logarithmic mean, that is nothing but log K2 by K1 divided by K1 to K minus K1. This is called as a log mean. You get one more mean, geometric mean. Geometric mean, if there is a progression A, B, C in a progression, then the geometric mean B is a root of A into C. That is what the geometric mean is all about. So here the logarithmic mean, this is nothing but a logarithmic mean. So combining this 14 with the 10, you get the maximum concentration of R. Cr max divided by Ca naught is this particular equation. This is a very important expression. In the problem, they'll give you K1, K2, and you have to find out Cr max by Ca naught. This can be asked for 2 marks, or if they can ask for a derivation and a problem can be asked for 16 marks. Yeah, any doubt? So this logarithmic mean you get, earlier you had this logarithmic mean. Can anyone tell where you got this logarithmic mean? Logarithmic mean? LMTD, heat transfer, especially heat exchanges. Did you get it? Logarithmic mean? Not only here, even in mass transfer, you get logarithmic mean, especially the diffusivities first unit, mass transfer one. Can anyone tell why we are taking the logarithmic mean instead of an arithmetic or other means? Anyone, any idea why we have this logarithmic mean? Especially even in heat exchangers, you get a logarithmic mean temperature difference, LMTD. You won't take arithmetic mean because you are having concentration. That is, this is a heat exchanger, and if you look at this curves, this is the temperature and this is the delta T, that is the length. So you get one thing like this and the other goes like this. That is, this is the hot fluid, this is the hot fluid loses the heat, the cold fluid gains the heat. So this is the temperature inlet and this is the temperature outlet, this is the temperature inlet of it and this is the temperature outlet of it. So you go for a delta T, that is the logarithmic mean. Why we go for here? Any idea? Especially heat exchanges. Anyone can tell why we go for instead of log arithmetic mean, why we go for log mean? Any idea? Any idea? Even in mass transfer also you get a log mean. No idea? Yeah, some of you tell whether it is idea is there or not. I'll give you the answer. Yeah, any idea? Well, at least talk something. Otherwise, I'll leave it and then go, right? It's not that you come here and sitting or chatting something. Yeah, I need some feedback. What is happening? No one is going to talk. Don't want to talk.
Sir,
Yes.
Sir,
if the
What
graph
happened?
is not linear, we go for logarithmic mean.
No, I just want to know why you people are not don't want to interact with the faculty. You come here to learn, not to do something, right? At least some of you should tell, right? But no one is answering anything. So if you are doing like that, I will just run through the presentation. Later, you should not tell that we didn't understand or something like that. CRE, again, I'm telling you, it is one of the difficult exam of what do you call chemical engineering. Again, I'm repeating to you. I'm going damn slow. Still, I'm having half of the portion in the first unit. Now, this is my 12th, 13th class, right? Still, I require 13 more periods for the first unit to cover. If you are silent, then I'll finish off in 2 periods. Again, I'm telling you. Don't try to test the patience of the faculty. If you are quiet, then I'll finish off in 2 periods. That's all. I have to know, right, whether you are listening to me or something like that. Again, I repeat to you, without a faculty help, it is very difficult for you to read the CRE. So you may be having some things that you can read on your own or something like that. Okay, then try to read yourself. Yeah, till all people answers, I am not going to move forward. Yeah, I'll just keep like this.
Sorry, sir.
What sorry? How many times you people will tell sorry? This is not the first time is happening. Earlier also I warned you, all the people. I'm not talking to only Tirtha or something. I appreciate her, at least she opened her mouth. So what I am talking is for all the people, not for only for Tirtha or some Guru Prakash. Yeah. This is not the way to be taken. I am again repeating to you. You are in the 3rd year, right? Again, I repeat to you, if you are quite like this, I will finish off the entire syllabus in just 10 periods. Just 10 periods is enough for me because I'm having that experience to take lengthy or even shortcut also. So since you are not hearing, just I want to finish off my work, I will just finish off my work. Again, I repeat to you, CRE is not an easy subject. Not only CRE, even whatever you get in this 5th semester, mass transfer, even thermodynamics, all the very core subjects. Okay, forget about what do you are unfit to be. Yeah, this is CR max by CR naught is K1 by K2, this particular thing, right? So in the problem, they'll give you K2 values, K1 values, and they'll ask you to write the essay, what do you call, 2 marks question, or they can give you this problem as an derivation for an assignment, right? So next we go for an autocatalyzed reaction. An autocatalyzed reaction is a reaction in which R is the one of the product will act like a product itself will act like a catalyst, right? So A plus R gives R plus R. R is the product. So R itself is acting as a catalyst. So example, you can give curd. If you want to make curd, then you add curd to the milk, then it will give you, right? All biochemical reactions almost, it is autocatalyzed reaction. So this kind of thing, how to do? Again, Ra is minus dCA by dt, K1, K into CaCr, the same. So at any time, we know that initial concentration of A is Ca plus Cr or Ca naught plus Cr naught. That is the initial concentration of R and S, or at the final concentration. So that should be constant, because how much of R, a small amount of R is required. So this should be constant. So if you differentiate this, we know that Cr we can write as C is naught minus Ca. So you take all the Ca terms to one side and then integration. This should be done as a 2ab. So you go for a partial fractions and then calculate this A and B. So if you do that, then you are land with integral Ca0 to Ca dCa by Ca, this particular thing. So the partial fractions are just 1, 1. A is 1 and B is 1. So you try to find out the integral. This is the integral and substitute the limits. This is the integral for this, because C0 is constant. No need of doing any integral for that. So you are doing only with the Ca. So substitute the limits, then K Ca0 T. So this is log A into log B. So you can multiply and then put it. We can use C0 is Ca0 plus Cr0 is this. So try to eliminate some of the thing. You can write Ca as C0 minus Cr, like that Ca0 is C0 minus Cr0. So using this condition. So substituting that, Ca is C0 minus Cr and Ca0 is C0 minus Cr0. Then we are landing with one big equation. Ln Ca0 by Cr Ca Ca0 is this particular thing or this particular thing. So if you put M as Cr0 by Ca0, that is the initial concentration of R and A, and Xa is the fractional conversion. Then you do again, this is the differentials, because you need to Ca0 minus Ca C0. So you have to do the differential for A into B. So A into differential of this and this into differential of this. Otherwise, Ca you are writing C0, we can write as Ca0, Cr0. Ca is Ca0 into 1 minus Xa. Then try to take something common so that you get some simplified equations, right? So like that, Ca naught into Ca minus Cr is Ca naught square M plus Xa, where M is Cr naught by Ca naught. So do that again, still because you are having some more thing in the down, Ca naught minus Cr. So do that again, substitute it, and then you are left with final form of the equation is this. This is a very important equation in terms of M. Oh, sorry. So in terms of M, this is the big equation. Whatever. So, bear with me. Yeah. This is the equation. And if you draw this on the y-axis, this on the x-axis, that is what I'm doing. That is what, or this particular thing, you get a straight line. The slope will be equal to Ca naught M plus 1 K, right? Here, one important thing is Xa, if you draw Xa versus T, only verum Xa versus T, then you are left with this particular curve, like a S-shaped curve. Lower rate will be there. There will be a higher rate and then a lower rate. You get a S-shaped curve. Why we get a S-shaped curve? Because here the equation is A plus R is giving you R plus R. Initially it is A gives R. A should give R, but some amount of R should be there. Little amount of R, more amount of A is there. Therefore the rate will be less. Then after some time, what will happen? R is formed. Therefore, more of R is as a raw material, because you are not taking it. This is a batch process. So R is inside in the batch reactor. So R is more formed. Therefore, A reacts more with more R to give you more R. Therefore, the rate will be at its highest. And then afterwards, what will happen? More R is formed, but A is disappeared because more R is formed. So A should be less. Therefore, less amount of A is there. Therefore, the rate will be very less. And if you draw the reaction, that is rate of a reaction with this particular thing, you are left with, you start with R, somewhere R is present because some of the R should be present. Your rate will decrease, or the rate will go on increasing till a maximum, and then rate starts to decrease as A is being more, A is consumed. Because here initially it is increasing because AR is formed, therefore more of the product is formed. Afterwards, what will happen? With progress in time, since A is more, R is formed, the amount of A is less, therefore it decreases. This is actually going in this direction. That is why you put this, right? So we need to find out, there will be some maximum thing which is there. So you need to find out this particular thing, again differentiate that, and then equate to 0, you get that maximum, right? This is what with the auto catalyzed reactions. Very important 2 marks question will come. A reaction in which one of the products of the reactant acts as a catalyst is called as auto catalyzed reaction. So one example, all biochemical reactions you can give, or this curd also, milk with curd also you can give, right? Anyhow, you won't talk, so I don't want to ask your feedback. So let me continue with the next one, reversible reactions. I'll show you how, if you are not responding, how I will go, right? So next time onwards, if you are not responding, this is how I teach, right? So A is giving you R, and again R is giving you A. So K1 is the forward constant and K2 is the backward constant. So this kind of reactions, till now we had only like irreversible reaction. So we need to do with a reversible reactions. So net disappearance will be forward minus backward. So you can write with respect to disappearance of A or appearance of R. So K1 Ca, K2 Cr. We take M as Cr naught by Ca naught. That is the initial moles of Ar to the A. So at any constant, we know that Ca is Cr naught into 1 minus Xa, and Cr is Cr plus, because this is the product. So you get plus, and this is the reactant, you get minus, right? So if you differentiate this, minus dCA is Ca naught into dXA, like that you can differentiate this also. Then minus dCA is Ca naught into dXA, K1 Ca is Ca naught into 1 minus Xa, minus K2 Cr you are writing like this. At any equilibrium, net rate is 0 because it is forward reaction is equal to the backward reaction. So we differentiate this equation because at equilibrium the net rate is 0. So we differentiate this with and equal to 0. What you are getting Xa as Xae, that is the equilibrium conversion. So if you do this differential to this, then this is 0. So do the differential for this. Ca naught is constant. So K1 1 minus Xa, K1 is constant. So you have to do the differential with Xa. So 1 minus Xa is Xae, that is what he is putting. Minus K2, this is M into, because Cr naught we are putting as M as Cr naught by Ca naught. Then you can put Cr naught as M Ca naught. So M Ca naught is there. So you take it out and then put that thing. So M plus Xae. So if you equate this, you are getting K2 as this particular thing, or K1 by K2 is this particular thing. One important thing is Kc, that is the equilibrium constant, is nothing but Cre divided by Cae. That is the concentration of R at equilibrium divided by the concentration of A at equilibrium. So if you do all that here, K1, K2, K2 you are getting. So, and if you substitute back, dxa is this. Either you are putting in terms of concentrations here, or you can put in terms of conversions also. This is what the conversions is all about. So if you do that, dxa, K1 this, K2, K2 is nothing but we already got a K2 in terms of K1. So you substitute that K1 this into M plus AK. So take cross multiplication and then do all this. and then you are left with you are coming with this particular thing. Integrate this. This is in terms of XCS and T, whereas the earlier thing you are doing in terms of CS, right? So XA is the equilibrium. XA is the thing. So equilibrium is constant. So you have to differentiate or integrate with respect to XA. So if you do final form, this is the expression which you get. It's a very important expression. So either you can write in terms of conversions, or you can write, sorry, this is conversions and this is concentrations. That's up to you. Both you can write. So if you plot this versus this time, this is y is equal to mx. So the slope will give you, that is what, k1 m plus 1 by m plus xe. Either y-axis can be concentration or the conversion, right? So this is what the reversible reactions is all about. So once we have all the reactions, we discussed irreversible reaction, reversible reaction, and multiple reactions. For a constant volume only we did till now. The volume can change. The volume can change. This is for a if you want to compare, you can compare for a reversible first order and a reversible irreversible reaction. This is for irreversible reactions, whereas reversible reactions, yeah, so this is for irreversible reaction. For a reversible reactions, you are getting this. If you assume this is CR naught is 0, then you are left with the same equation, right? So whether it is reversible or irreversible, reversible can be converted to the irreversible process. If you substitute, there is no back reaction. So like that you have to do for second order also. It becomes very difficult. I'm not that telling you it is easy, because you know for a normal reaction itself how difficult it will be. If there is a reversible reactions, it becomes still difficult, right? So you are left with this particular equation for especially bimolecular second order reactions. If you want, you try, but again it is difficult. So some of you can try, and if any difficulties, you can talk to me. So that's all about this. Till now we discussed with what do you call constant volume. We have to go for what do you call the other one, that is variable volume, right? So if there is a variable volume, what will happen? Because this V, earlier we are writing like this, A gives R, this is K, minus RA is minus 1 by V into dNA by dt is like this we are writing, right? So the rate of disappearance of A is minus 1 by V into D, that is the number of moles of A disappearing, to that of T, that is equal to K1 or Ca or whatever you are writing. Now, since this V is constant volume, you are taking inside this integral. Then what you are doing, minus d of Na by V by dt you are putting. That is nothing but Na by V minus dCA by dt. That is what you are putting. For a constant volume, you can take inside the integral differential, and then you can integrate it. But actually, if there is a variable volume, you cannot just like that take the constant here. Understand? So this is not a constant. This is changing. This is changing in terms of this. V is V naught into 1 plus epsilon A XA. So V naught is the initial volume, 1 plus epsilon A XA. XA is the conversion, and epsilon A is a fractional change in the volume. Fractional change in the volume, which you can calculate by using volume at final conversion minus volume at that is volume at final conversion minus volume at initial conversion divided by volume at initial conversion. So at an initial conversion, your XA is 0. At a final conversion, your XA is equal to 1. So V of Xa is equal to 1 minus V of Xa is equal to 0 divided by this. Or you can put epsilon A as change in the total number of moles for a complete reaction divided by the total number of moles fed to the reactor. To give one example to this, how to calculate this. So if A is giving you 4R, your epsilon A is volume at final conversion. What is the volume number of moles at the final conversion? 4 minus the volume at the initial conversion is 1 divided by the volume at the initial conversion, that is at a 0 conversion is 1. Therefore, it is 3. So you have to put 3 here and then do that. And if there is one more, A gives 2.5 R, then what is your epsilon A? Epsilon A is 2.5 minus 1 divided by 1 is 1.5. So this is the expansion coefficient 1.5, right? So this particular thing should be included. When you have this included, you get the extra term in the integral. So already you had some 2 terms in the integral. So if you have this, you get 3 terms in the integral for the normal first order reactions. We'll see that. So the rate of change of component I is Ri is 1 by V dNi by dt. So Ri is Ni you can write as Ci into V, because Na by V is concentration. So concentration Na, if you want to write concentration into V, we can put. So this is in the form of derivative of A into B. So A into derivative of B plus B into derivative of A. That is what we do. B into V into derivative of Ci plus Ci into derivative of V. So here already V is there. You take it inside. So this cancel. So Ci by V you get. So this is what you are getting. Earlier Ri is minus dCi by dt you are getting. But here for a variable volume, you get this extra term into picture. So that comes because of this. V is V naught into 1 plus epsilon A Xa. So I gave one example. Now we can do for this, keep it for some time. I'll again talk, because A is giving you 4R. If A is pure A, then you are getting expansion factor as earlier case is 3. But if there are some inerts present, only 50% of A is there and 50% is inerts, then how to calculate this epsilon A? It will be half of it, that is 1.5. So this particular thing I'll do when we do some problems. I'll explain to you how to do that, right? So like this, you have to do. So here itself, let me put here so that forget about this. How to do this, I'll just show you. Please write in your notes so that it will be easy. A is giving you R. So this is having some 50% of A, 50% is inerts. So how to do this is like this. V Xa is equal to 0. So you have to make a tabular column. You make a tabular column like this. So this is A, this is inerts, this is R, and this is the total, right? So initially R is 1.5 because 50% is in it. Inert is 0.5. R is not there. The total will be 1.0. V at Xa is equal to 1. That is a final conversion. The final conversion. This is 0.5. This nothing will be there because the entire A is getting consumed. How much R is formed? This let it be 4R, right? So how much of R is formed? R is formed is 4 times, because R is 4 times 0.5, because only 0.5 is there. So that is equal to 2. That is equal to 2, right? So 2 plus 0.5 is 2.5. 2 plus point. Now, what is expansion factor? That is V at XA is equal to 1 minus V at XA is equal to 0 divided by V at XA is equal to 0. So epsilon A is equal to V at XA is equal to 1 is 2.5 minus 1 divided by 1, that is 1.5. The same thing. You can do this way also. 50% mole of A. Therefore, 4 times 50 is 200 moles. Then the 50%, 50 moles is inerts. So initially 100, final is 250. So 250 minus 100 divided by 100, 1.5. This way also you can do, or this way also you can do. So you can do like that for, now A is giving you 3R, 75% of A is formed. So let us again put here Vxa is equal to 1, Vxa is equal to 0. This is A, this is I, this is R, this is total. So V at Xa is, this is 75% of A is there. So 0.75, 0.25, nothing of R is there. Total is 1. So V at Xa, sorry, this is 0, this is 1, sorry. So at Xa, this nothing will be there. Inerts won't take part in the reaction. R is 3R, therefore 3 times what is R? 0.75. So how much it is? 0.75 into 3? I think 2.25. So how much it is? 2.25? 0.25. Therefore 2.5 is the total. So XA is Vxa minus is equal to 1 minus Vxa is equal to 0 divided by Vxa is equal to 0. Therefore, Xa is equal to 2.5 minus 1 by 1. Therefore, 1.5. Like that, you can do for 40 mole percent, 90, 55, all that, right? So this is one exercise for you. Then let us do for a zero order reactions. For a zero order reactions, how to do this equation? That is, A is giving you R. This is K. So you are writing as minus RA is K times Ca power 0 is minus dCA by dt. Right? So this is the expression. That is what we are doing here. Minus RA is minus 1 by V into dNA by dt. V is nothing but V naught into 1 plus epsilon A XA into differential NA is NA naught into 1 minus XA by dt is K into Ca power 0 because zero order reaction. So you see V naught is constant. So here Na naught is constant. So Na naught by V naught is Ca naught. That is what you get. The rest of the thing, this is not a constant. So that you are keeping. So this A is coming out. So differential of 1 minus Xa by dt. So Na naught by V is Ca naught. This you keep it. So this differential is minus dxa by dt is K. So take all the K times to one side and D times to one side. So Ca naught dxa by 1 plus sigma Axa is Kt. So put the integrals, limits, in between the limits 0 to Xa and 0 to T. So you are left with this particular thing, right? So this is the expression which you get. So to substitute this, this is 1 plus something. So you need to put, let it be some y. So if you differentiate this, then dy. So dxa is dy by, so you're changing into y and then coming back into things, right? So it's just a differential. So this is the final form of the equation. Ca naught by Xa, ln V by V naught is Kt. So if this depends, if you draw a graph T versus ln Va by V naught, so it will have a positive slope or a negative slope. It depends on the expansion coefficient. Sometimes if A is giving you R, 4R, you'll get a positive quantity because 4 minus 1 divided by 1 is 3. So if there is a positive slope, you get a curve like this. Sometimes what will happen, 2.5A gives some B. Then if you do this 1 minus 2.5 by 2.5, then this lands you to negative value. So you are getting like this. So this we call it as an expansion, and there is a change in decrease in number of moles. If there is a decrease in number of moles, that is final moles is less than the initial moles, then you get a negative. So you get like this. Okay. This is for the zero order reactions. Like this, you have to do for a first order reactions. Again, first order reactions minus RA is V instead of V, we are putting this Na naught by V naught is Ca naught. Earlier, you are getting only Ca naught, C naught. So you get this 1 by epsilon A XA into picture. So if you do that, minus ln 1 minus xa is this is for a reversible reactions, irreversible reactions with what you call no expansion factor. When there is a variable volume, you are left with this particular equation. So extra term will come into picture, epsilon a. That is what you try to do, right? So like that you can do for a second order reactions. It becomes very difficult because you get a square term now. So it's not that easy again because you get one extra term in the denominator. Yeah, try to do with zero first and second order, right? So in the next class, we'll do some problems, right? This is all with, we completed the entire unit now. One class, I completed the entire unit. That's all, right? So you having this particular thing, we did with the reversible reactions, we did with irreversible reactions, we did with a constant volume, we did with a variable volume. So whatever you are getting, whatever may be the order, different equations will come. So based on that, you have to use in the problems, right? So that problems we'll do in the next class. Now already it's time. I'll stop here. Yeah, any doubt you can let me know. Yeah, anyhow you won't have any doubts, right? Because you know you are not listening to me. You kept in your mind that we should not talk or we should not communicate with any professor. Okay, you keep yourself, no problem. Okay then, thank you. I was very disappointed today. I didn't like the way I'm taking the class, but if you are not responding, this is how it will be. Each period, one unit will be over, right? So my job will be done. Okay. Yeah, now 58 people are there. Guru Prakash, you take the attendance and then send to me. I stop the sharing now.